The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Just before the break, we were talking about the need for a light amplifier, an optical amplifier, to make a lasing possible. All right, so here where we left off, we had the cavity or the resonator that gave us these modes, and the spacing between them is C over 2L, as we mentioned. And now we put the amplifier within this cavity to overcome the losses. And I say, in general, the losses come from the mirrors. And if there's enough gain here, let's say this is the location of the gain in frequency, and if there's enough gain at this cavity resonance, then we will get lasing, and we'll get light output by making this mirror not 100% reflective, but has a little transmission in this mirror here, so we can leak some of the light out. So then the spectral width of the laser then narrows down from initially this to this essentially this delta function, this delta f going close to 0, and then in the time domain we get, as a result of this narrowing, we get a wave train that's a pure sinusoid, constant in frequency and constant in amplitude, and that's the sort of the output of a typical, what shall we say, an ideal laser. So now, if somebody then asks you why does a laser have a very narrow spectral width, then one can then say that it comes from the fact that we have an optical amplifier, within a resonator with enough gain to overcome the losses to give us this extremely narrow line width. Now, I'm going to then tell you about how the next property, the one that has to do with diffraction limited collimation and focusing and so on, where does this property come from? Again, in a simple-minded way at this stage, and later on we'll go into it in a little bit more depth. Well, the spatial properties really come from the fact, of course, that we have an amplifier within the resonator, and we have these two mirrors. Let's take two plane mirrors, for example, and we'll see later that indeed the mode that can be supported within that cavity is essentially a parallel beam that gets reflected backwards and forwards between these two mirrors. And the amplifier then overcomes the losses in the cavity, and this mirror has a little transmission. So the output here you would expect to be a collimated beam, a plane wave, with diffraction limited collimation, and if you put a lens, will be diffraction limited focusing. Now, not all laser cavities have plane mirrors. Some of them have curved mirrors, like in this case, two concave mirrors. Again, the mode shape, as we'll see later, will be different from this, will be something like that. And then if we let some of the light leak out through one of the curved mirrors, you'll see it will be diverging. Just because it's diverging, it doesn't mean that it's a bad beam. It just means that with lenses, we can convert it to any size beam we want and focus it and so on. So it's the cavity plus the amplifier that gives us this very uniform wave that we talked about before. In fact, if we can shape the output of a laser beam, is these two outputs, excuse me, with lenses, and then we can create here some small focus spot, here maybe a slightly bigger focus. We can then create a narrower collimated beam from what we started with, or a larger collimated beam, and so on. It's all done with the use of good optics outside the laser cavity. So this all these properties to do with the spatial effects of the laser beam then come from the cavity plus the amplifier. All right. Now we want to talk about where does high power come from. Excuse me. Well, the high power comes from obviously, from the amplifier, because it's the amplifier that gives us gain to overcome the losses, and if we have more gain left, then that can be converted to power out. So the bigger the amplifier, then the more power we'll get. As simple as that. So later we will find out about how an amplifier works. So if we can come up with a bigger amplifier and how to make a big amplifier, then we'll really know the secret of making high power lasers. So it's in the hands of the amplifier. The tuning range. Where does the tuning range come from? Well, let me give you again a very simple explanation. Let's go back to the laser that we had, two mirrors separated by distance L in a cavity, and then we had the cavity mode over here, and then this is the amplifier bandwidth. This is where the amplifier likes to provide gain. And then we said that the output of the laser would be this delta function at the cavity resonance. Now, these modes here are not fixed because they depend on L. So if I change L, the length of the cavity, I can move these modes around. So if I move this cavity mode around, if I move it just a little bit here, then this frequency here will be dragged. The laser frequency will be dragged with it. And the tuning range is really the width of the bandwidth of the amplifier. Because if I tune the cavity outside that, I get no output at all. Now here is an amplifier that has a bandwidth that's bigger than what I showed you before, which means now that the tuning range can be wider now. Okay, depending again, as I say, on the bandwidth of the amplifier. And if in this particular case, if this mode leaves the amplifier at this end, there's the other one that will come in. So I will always get some output from the laser, but the intensity can vary depending on where I am with respect to gain curve. While over here, in this previous one, if the mode is outside the amplifier bandwidth, I get no light output at all. So then in summary, then the tuning of a laser then depends on the bandwidth of the amplifier. The wider the bandwidth, the wider the tuning range. Okay. So now the remaining property that we talked about before is the very short pulse width generation. So the question is, where does this come from? Again, in a simple-minded way. Again, here to explain this, I need to give you a little bit of a background, and then start with what we've done before. If you had a delta function in frequency space, in the time domain, you have essentially an oscillation, a sinusoidal oscillation with a constant amplitude and a constant frequency. This is what we've been talking about before. Now, if I looked at the intensity, remember this is now at optical frequency, maybe 10 to the 15 hertz or so. So it's a very high frequency. I cannot observe it. I don't have any way of observing it. But if I looked at the intensity associated with this using a square law detector, what I get is essentially a constant output, constant intensity output associated with this wave. So if I have then a delta function in frequency, I have then intensity would be constant. So this is completely opposite to generation of short pulses. This is essentially a CW laser. But now let's see what happens to this constant output when I add another frequency. If I have now two frequencies, let's say that are oscillating, one at f1, one at f2. Here they are, difference in wavelength, a difference in the frequency, separated, let's say, by f sub s. Now, when I combine them and look at them in the time domain, I get something like this, which is like a beat frequency, or is a beat frequency. The period between these peaks, t, big T, is just simply 1 over f sub s, the separation in frequency. But if you look at the intensity associated with this wave, it looks something like this, which is the envelope of this beat. It's no longer constant just by simply adding two waves of different frequencies. And we're all familiar with beating effects of when two singers sing with two different frequencies, then you'll hear the beat. So basically now I've transformed a constant intensity to a sinusoidal intensity. It's not quite a short pulse yet, but it's sort of getting there. All right. So now let's look at let's look at what happens when we add another, yet another frequency. All right, here it is. Now we have three, F1, F2, F3. Here they are in the time domain. I add them up, and they give me some waveform like this. When I square this, I get the intensity to look like this. As you can see now, this width is beginning to look like a pulse, but again, not quite. Again, the repetition between these two peaks, the period between here and here, or the time between the two peaks, or the two sort of pulses at this stage, is again 1 over Fs, where Fs is the spacing between these modes, and we're assuming they are constant spacing between these frequencies. Now you can think you can add more and more frequencies, and let's see what happens. Now I've simplified the picture, and I just put the intensity output that we've had before. Remember, when we had only one, it was constant intensity. When we had two, we have this sinusoidal behavior. 3 is like this. 4, if you add 4, it begins like this. 8, if you 8, now it's beginning to look like a pulse. And then when you go to 16 frequencies that are constantly spaced, then indeed it begins to really look like a pulse. The period, okay, the separation between these pulse strains is again 1 over Fs, the frequency spacing between the modes. And the pulse width, which is the key thing here, the pulse width is given by 1 times n, the number of modes, times f sub s. So n times f sub s is really the total separation in frequency between the first and the last frequencies or modes. All right. So then you can see here that the shorter the pulse, all right, if you want a very short pulse, then you want to make n times some Fs very large, which means either n is very large or f sub s is very large, or certainly the product has to be very large. So when that's the bandwidth of the essentially the of the spectrum of these modes. So the key thing then is to have, let's say in this case, lots of modes extending over a wide frequency range, and then that would give us this short pulse width. All right. Big question now is, where can we find all these frequencies in a laser? All right. So let's go back and remind ourselves what we just mentioned about lasers. We said that if we have a wide gain bandwidth gain medium amplifier, and we have then lots of modes, lots of cavity modes under this amplifier, then, and if there's enough gain to overcome the losses in all these modes, then I would get essentially four frequencies. Well, before we only talked about 1, but now I can generate 4 frequencies out of this amplifier, if the amplifier allows me to oscillate at all these frequencies. That's all very nice. So we can see that this is the beginning of having many modes. So if you can imagine an amplifier that has much bigger bandwidth than this, then I can have more and more of these modes oscillating. All right, and then so of course, if I have, just to remind you, if I have 16 of them, then essentially and a certain spacing between them, but basically I can get a narrow pulse coming out of the laser here without essentially doing anything. Now, I didn't mention a certain key issue here, and that is when, and we can go back and show you, when I combine the sine waves. Let me go back to this view graph here. When I combine these sine waves here, these waves had to be in phase. Somewhere they had to start together. And if they don't, then you wouldn't get this kind of behavior. Because if the relative phases are way off and different, then you're in real trouble. So let me see if I can find my view graph here. And this shows that what happens when all the 16 modes, in this case, are all in phase or start together, then indeed this is what I'll get. I get this pulse width as given by 1 over NFS. So this is a special condition I have to satisfy in order to generate this narrow pulse width. And here's an example. What happens if only 10 of the 16 start in phase? and not all 16 of them, then I get a messy looking output like this, and it's not like this at all. So in order to generate very short pulses out of lasers, then I need to get all these modes under the gain curve to start together. And that is the topic of phase locking or mode locking, and we will talk about that later. So lasers can generate very, very short pulses only if you can get all these modes to go, and they have to start together. They have to be phase locked or mode locked, and so on. And with that, that's the output of the laser becomes the series of short pulses, and if the bandwidth of the amplifier is very, very broad, then you can get these short pulses like picoseconds and shorter. All right. So now we've talked about, so far we've talked about the unique properties of lasers. We talked about, in a simple way, how these properties come about. Now we're ready to put all that stuff together and see how a typical simple laser really works. All right. So now let's start talking about the simple laser. So here the title of this session, as I had before, is the operation of a simple laser, and I have even a demonstration for you at this stage. The lasers that we have, simple ones called helium neon lasers, and because the amplifier is a helium neon amplifier, and we'll talk about how that works in a little while. Now here there are two kinds of lasers. One where the amplifier tube is terminated by the two mirrors, and the called internal mirror laser, and the other one, and this is quite typical for a lot of lasers, where the amplifier is terminated separately, not at the mirrors, and the mirrors are again separated from the amplifier. And usually these are windows called, there's a funny angle of Brewster windows, so that to minimize reflections. Again, we'll mention that later. But basically here, what I would like to show you in this demonstration is simple lasers like these. Now this one here, for example, it can't do very much because it can't adjust anything, it's all fixed. But this one here, if this mirror is on an adjustable mount, then I can adjust it and move the mirror around, misalign it, and so on. You can see how easily it is to stop the laser from lasing, and also what happens as a function of mirror adjustment. So let's now go to the demonstration number one, which is essentially on the on a simple-minded laser, and show you how it works from close. So now let's go look at this demonstration. Now we're ready to take a close look at a laser and see how it ticks and why it ticks. We've picked on a helium neon laser because a helium neon laser is a very simple one, and also it's one of the first lasers. In fact, the first laser was the ruby laser, and helium neon was right after it. So it was the second laser action that was observed. Also, the red light from a helium neon laser is familiar to almost every one of you, especially when you go to the supermarket and see it at the checkout counter. Usually a helium neon laser, a red helium neon laser is used. So let me start by showing you what a helium neon laser looks like. Here is a helium neon laser, at least a helium neon laser. They're all different. Now, what I would like you to see here is that it's made up of a discharge tube, which is this, which is the amplifier that is necessary for laser action. And then the discharge tube is terminated by two mirrors. Here's a mirror on this side. You can see it. Here's one mirror, and here is the other mirror. Okay? So it's a this is a small laser, and the mirrors are sealed right onto the discharge tube. Now let's see this laser in action, and we have it already set up for you over here. And then all I have to do is to turn the power supply on and count to 5, and the laser will come on, and here it is. Laser's on. You can see here is the glow in the discharge, and you see a pink streak, and that's where the light goes backwards and forwards and gets amplified. And here is the output mirror. The other mirror is sealed, and the output from the mirror here then goes onto the screen. And that's it. As long as we power the discharge and have enough gain to overcome the losses, and we choose the mirror transmission appropriately, you'll get laser action. Now, with this kind of a laser, it's very difficult to adjust anything and to play with it. So what I'm going to do, just so that you can see a little bit more of how a laser works, I'm going to go on and have a laser that the mirrors, in which the mirrors are external to the tube. Now, in order to separate the mirrors out from the amplifier, from the discharge tube in this case, we have to seal the discharge tube. Now, here is, you can see here, if we take a close-up at this, here is a sealed discharge tube. It doesn't have mirrors on it, but has windows. Let me show it to you again. Here's the amplifier section, and here is the cathode, and the anode is over here. So the discharge then runs along this line over here, okay, this capillary tube over here. Now let's focus at the ends. We don't have, as you can see, we don't have square mirrors. You can see we don't have windows, I should say, not mirrors, because we're going to have the mirrors external to the discharge tube. But you can see that the windows are sealed, but they're not square to the tube. And the angle, in fact, is called the Brewster angle, because at that angle there is no reflection from the glass surfaces for a certain polarization. So that's why one uses windows at the Brewster angle, so that there is no reflection in the windows. And you can see both ends. Now if we take a look at the other end over here, a close look at the other end, you see that again both windows are at Brewster's angle. So here is then the amplifier tube, and now we have another one, a similar one, that is placed, and I'll position it in the same way, that is placed over here, that held in place over here in this setup, and there's wires running to run the discharge. So here is then the amplifier tube inside this laser, and let me again point to the mirrors now. Here is one mirror, and here is the other mirror. And each mirror is held in a hefty mirror mounts, and the adjustments are over here. We have two adjustments over here, and then we have similar adjustments over here. All right, so here is then the tube, the amplifier tube. The windows are terminated with windows at Brewster's angle, and then we have the two mirrors. So now I'm going to turn the discharge on, and here it is, and let's see if the laser is lasing. All right, so if I put a card here, you see that indeed the laser is lasing. So what I'm doing here is reflecting it by this mirror here, then this mirror here. Here's the laser beam, and again onto the screen. So on the screen now, we have essentially two spots. One is coming from the laser with the fixed mirrors, that's this one, and then the other one, the other spot is coming from the laser with the adjustable mirrors here. So what I'm going to do is first block the laser with a fixed mirror so that we don't have any confusion, and the only spot then is from the laser with the adjustable mirrors. So now here we are. Here's the laser then, all opened up, and now I'm going to show you how touchy the alignment is. So now if you watch the intensity on the screen as I slightly misalign, you can see the light is out already just by very small misalignments. So here we are, it's a peak value, and then I go the other way, and it's gone. So the alignment has to be very, very stable. All right, now I can also adjust horizontal alignment. Again, show you how touchy everything is. So here we are. Here is then, in a nutshell, here's the amplifier section. The longer it is, of course, the more gain we have, and the mirrors are placed, in this case, about 50 centimeters apart. This one is a flat mirror, and this one is a spherical mirror, and the alignment has to be very stable, because a small misalignment would create a lot of loss, and then we just don't have enough gain in the amplifier to overcome these losses, and the laser quits. I hope you've enjoyed watching this first demonstration on what goes on inside a laser. Of course, the key thing is the amplifier. And now I think we need to talk about how does a light amplifier work. So this is what I have now for this next topic, is that how does really an optical amplifier really work? So what we mean by an optical amplifier, we need light going in to this magic box here, and we need the light enhanced or increased or amplified at the other end. So the question is, what is this magic box here that takes light from one end and actually amplifies it and sends it out at the other end? All right, that's the key question. So in order to answer this, we have to see what we understand about the interaction of radiation or light with atoms or molecules. Right? So let's start with that. Now, we're very familiar, for example, with light interacting with a material and getting absorbed. That we see that all the time. That's sometimes completely absorbed, and sometimes it's not completely absorbed. Like a piece of glass, for example, if you send light through a piece of glass, if it's uncoated, normal incidence, and so on, you lose about 8% or so for both sides. So other materials will lose more. And we see that all the time. All right? So first, let's understand what that is. Once we understand what absorption is, then let's see how then we can understand amplification. So we'll start first by looking at absorption. All right, so here is in order to understand absorption, we need a model for the atom. All right, and as I say, in this course, we keep everything very simple so that we can get a basic intuitive kind of understanding of what's going on, rather than complicate things with a lot of math. Now, a model for an atom, all right, is where, let's say, an atom has several energy levels or orbits or what have you, and the atom, here's the ball, here's the atom, is in its ground state or lowest energy state at the beginning. And all atoms essentially are at their lowest energy states at the beginning. Now, when light comes in from over here, let's say these are two photons coming in, they will interact with the electrons, let's say in this atom, and will excite the electrons to some higher state or even higher states. In this case, I'm only taking a very simple model, just two-level system. Now, if the light wavelength or light frequency is not correct, the atom will not be, or the electrons here will not be excited at all. But if the light frequency or wavelength is a certain value, of a certain value, then the electrons here can be excited, and from now on I'm going to call it the atoms, can be excited from one level to another level. And when the atom is is excited from one level to another level, then essentially it takes energy from the light, or it takes photons from the light to get excited, because now the atom itself has now higher energy than it started with. And of course the light gave up its energy to the atom, so it has less energy when it leaves the atom. And this is generally called absorption. And then let's say a few more words about that. Here again, this picture that I had. In terms of just straight waves, here is a big wave coming in and a little wave coming out, and that essentially is absorption. I've labeled here E1 and E2 for the energy levels, and it turns out that the frequency where you get maximum absorption, or the wavelength or frequency you get maximum absorption, is given by the difference in energy, E2 minus E1, divided by h, which is Planck's constant, and that gives you the frequency at resonance. And if you, for example, put a detector out here, and you can see that as you tune the frequency of this light source, you have no absorption at the beginning. All the intensity comes through, and then when you're close to resonance, what you will see is you dip like this and back to no absorption. So over here there is some absorption, and this absorption occurs at this resonance frequency determined by the energy level difference divided by Planck's constant. Okay, the wavelength, of course, is proportional to that. As you know, frequency times wavelength equals the speed of light. So that either you talk about frequencies or wavelength. In this course, I'd like to talk about frequency because it's easier to talk about frequencies than wavelength. Now, if again, the amount of absorption will depend on the number of atoms or molecules that you have, and the width for the absorption again depends on the particular transition in that particular atom. Now, if you don't believe me, you can do an experiment, and here's how you might do the experiment. You take this variable wavelength light source and you send it into selected vapor, a vapor cell, and you put a detector at the other end. Again, you have now lots of atoms, let's say, or molecules. You send the light in, and some of these are going to be excited. You're going to go into this excited state, and the light is reduced, and that's what we call as stimulated absorption. And then we generate the same curve as we had before. So if you look at the output of the detector as a function of frequency or wavelength, then you would see this dip occurring at this resonant frequency. And this way you check out where this absorption occurs and the width of it. Now the interesting thing here is that you'll notice that if this is a glass tube, you'll notice some radiation coming out of the side. Now that radiation is when, you see, before the excitation, all the atoms were in the ground state, and that there was no radiation coming out from the side. But when you excite these atoms to an excited state, then another process comes in, and that's called spontaneous emission. Because these atoms that are in the excited state, in lots of cases, they don't like to stay up there. They like to come down. And when they decay, so-called decay, when they decay, they emit a photon in a random direction. And the wavelength or frequency of this photon is equal to the one that brought it up. So essentially the light that was absorbed from the original beam is now sent into all these directions. Okay, so now we've learned about what stimulated absorption is and what spontaneous emission is. Question is, what about gain? What we're after is amplification. All right, so let's see how amplification then comes about. Now, for amplification, to understand amplification of light, we reverse the picture. Instead of starting with the atom in the ground state, which where it likes to be normally, we're going to start with the atom in the excited state. So when a photon comes in, now there is no absorption that can take place, but what can happen if the frequency or wavelength of this photon is just right at the resonance frequency of this transition, then what can happen is that this light now will force this atom to come down. Because let's say there's no other energy levels to go up. It can even push it up. If there was an energy level here, then it could kick it up. But in this particular case, we say we only have two levels, so the only way for this atom to go is down. And then, of course, when an atom comes down, Remember, atom had energy up here. When it comes down, it will release a photon. Okay, so this photon, let's say, is the original photon here, and this photon over here is due to the release of the photon from this excited atom as it gets pushed by this source here. So now what we're seeing that we're getting two photons, okay, when coming out when we had only one going in, and as a result of the excited atom has been pushed down to the ground state. And this is the essentials or the basics of stimulated emission or gain, because now here you see that light can be amplified. All right. So let's talk a little bit more about this. As I said before, just like in absorption, the resonance frequency is again determined by the energy level difference divided by Planck's constant. All right. Now, in this particular case, if what you see when you watch at the output, you see that indeed the light increases now instead of decreases as we had before when you hit resonance. Again, the amount of increase will depend on, again, the number of atoms that you have, and the width will also depend on the transition of that for that particular atom or molecule. But the width is exactly the same as that in absorption that we had before. And in fact, the size of the gain is also, as I said, depends on the number of atoms, in this case, number of atoms in the excited state, and would be exactly the same as if the process were reversed and all the atoms were in the ground state, and the size of the absorption would be exactly the same as the size of the amplification, and certainly the widths are the same. And again, if you don't believe me, you do a little experiment, all right? And you do this little experiment here. You take a light source, and tunable light source, and now you send it into this amplifier. We're not saying what kind of amplifier it is right now, but basically it's a way of amplifying light. It's an amplifier that can amplify light. So again, you take this light source, tunable, you send it in, and you measure the output on a detector. Basically, this is the amplifier, has all the atoms, let's say, in this excited state. You send the light coming in, and if you hit the resonance, let's say we hit the resonance, and you start driving some of these atoms down, and the output is essentially going to be bigger than the input. Just like we said before, at a certain frequency, you're going to get the amplification of this light. Now, what about while we're at this, what about the spontaneous emission? Because before we said when all the atoms are in the excited state, there will be spontaneous emission. Well, that's true, because if you wait long enough, see, if you had a condition like this where there's no light coming in, all the atoms are excited, if you wait long enough, then all these atoms will decay spontaneously by themselves, emitting light in all directions. And that's bad news, because there's no more amplification. But when the light comes in, yes, it will interact with atoms and bring them down, and then the light will be amplified. But some of the other atoms here will also spontaneously decay and will emit radiation in all directions. And this is no good to you, because this light is lost and not available for amplification. So the whole secret then of amplification is to make sure that these atoms here are used up to generate gain, to come down driven by this field here, and not drop down by themselves and emit spontaneous emission. And that's a tricky thing, and you have to make sure you can handle that. Now, to summarize amplification is the following. We need let's look at loss first. When we have a lossy device, it means that we have, before we only talked about one atom, let's say in a state. Here I can put lots of atoms or molecules in, let's say, in the ground state, but fewer in the excited state. So if there's more in the lower than the upper level, then the net effect is absorption. So if N1, which is the number in the lower level, is bigger than N2, then the net effect is absorption. Gain is when there is more in the upper than lower. Because if N2 is bigger than N1, then we have net gain. And from now on, I'll be referring to it as a population inversion. Because normally atoms like to be in the ground state to start with and not in the excited state. So I have to, as we'll see later, I have to do something to put the atoms up here. and it's the net difference that will give me the gain. Okay, so now it's only a matter of how to put more atoms in the upper state than in the lower state that will give me the gain. All right. Question is, how does a laser start? So I have gain. So what? So I'm going to sit around waiting for the laser. How does a laser start? All right. So that's my next question. Is that how does a laser? Sorry, no, I wasn't looking at my. The question is now, I should hold off a little bit, but how to make an optical amplifier. And now let me just, I got carried away not looking at my visuals. Let me go back to fundamentals again. I have all the atoms, let's say, to start with here in a typical atomic system, molecular system. But I need, in order to get amplification, I have to have more in the upper than the lower. So I need a so-called pump. This pump could be, as we'll see later, could be optical field, could be a discharge lamp, could be a laser, could be collision, could be all kinds of things we'll talk about later. But basically, for now, let's call it a pump. And that pump, the job of this pump is take some of these atoms and put them upstairs here. Otherwise, you know, right now, it's like an absorber. This material acts like an absorber. Over here, it still looks like an absorber because you have more in the lower than in the upper. And as I keep transferring atoms from the lower level to the upper level, I get to a stage where, let's say in this case, I have 4 and 4, and it's neither gain or absorption. In fact, actually, the material becomes transparent. And even if I increase the light, doesn't matter, because the net effect is I have equal number in the upper and the lower, and we call that saturation, and there is no amplification or gain. So we started as an absorber, and with this kind of a pump, we created less absorption, but no gain. So in order to get gain, I have to do a little trick. All right. So this trick is the following. I cannot use two-level system. I have to use one more. All right. So we're going to complicate this by adding 3 levels to this particular atom or molecule. In this case, to start with, all the atoms are here in the lower level to start with, as usual. Then if I put this pump, and this pump again could be optical pump or whatever. This pump, if it resonates with the transition now from the first to the third level, it can take some of these atoms and put them up here. Now, if it puts them up here, as soon as you put some atoms up here, there is a population difference between level 3 and level 2. So now you have amplification for transitions for light at this frequency. But if you look at level 1 and level 3, that's still absorption or what have you, but certainly no amplification. So the amplification occurs as soon as you put one atom in level 3, because level 2 is empty. So you can create N3 bigger than N2, which is the condition for amplification, as soon as you pump one atom into this level. So the amount of gain that you'll get will depend, of course, on N3 minus N2, on the population difference, as we talked before. And there will be a constant that multiplies it that depends on, again, the particular transition, the particular atom, and so on. But the key thing is that it's a population difference. If N3 is not bigger than N2, then forget it, there is no gain. So the frequency for the amplification, for the amplified light, will be at this transition frequency, which is E3 minus E2 divided by H, which is Planck's constant. Again, if you want to do an experiment, then you do then this is the following experiment. You take again this amplifier, you take this tunable source, and the amplifier now has a pump. The pump then takes atoms from here and puts them up here and creates a population inversion. And then you tune this light source here, and then you'll see that when you look at the output, you see that again there will be amplification at this specific frequency that coincides with this transition. All right. So I'm sure now that after hearing me talk about all this, I'm sure you'd like to see that indeed optical amplification takes place, or the amplification of light takes place. And we have a demonstration for you, again using a helium neon laser as an amplifier. at least the helium neon part, as the amplifier, and we will measure. We'll actually measure amplification of light. We're all familiar with absorption and attenuation of light, but in this particular demonstration will be amplification of light. So I think now we're ready to enjoy this demonstration. So let's go and look at it. As we have already learned, the most important component in a laser, or the heart of the laser, is the gain medium, or the optical amplifier. This is no ordinary amplifier. This is an amplifier for light. And in this demonstration, we're going to show you, and hopefully convince you, that indeed light can be amplified. The amount of amplification is not so huge, but I'm sure we'll make it convincing enough so that you get the feel that indeed that light can be amplified. The setup we're going to use is here. We're going to have a laser, which is going to be our light source. Here's the output of the laser. We're going to reflect it by this mirror here, and then this mirror over here. Now, the laser beam then enters this optical amplifier. Now, this optical amplifier is essentially this. It's a discharge tube, helium neon gas mixture that will give gain, amplification or gain at 6328 angstroms. In fact, the light enters this window here and then comes out at the other end. And that's what we have essentially mounted here, right below. Okay? So then the output through this amplifier, and the amplifier right now is turned off, then goes onto a detector over here, and then the output of the detector then goes onto a scope, onto oscilloscope over here, and also we look at the output on a digital meter. All right, so we have two ways of looking at the same output. All right, now we're ready to set zero. All right, so first what I'm going to do is then block the beam of light over here, and let's look at the zero on the scope and the zero on the meter. Now, the meter says 008, which is not quite zero, and the reason for that is because we have room light hitting the detector. So what I'm going to do to get rid of that, I'm going to put this little hood over the detector. Now we see that the output of the meter now is indeed zero. And also, hopefully, then the output of the scope here, this will be our zero on the oscilloscope. Now, if I take this card away, let the light go through, you can see that now the output on the scope has changed, and the meter reads around 364 or 63 or thereabout, which is the output of the laser. Now, all I have to do is block the laser beam, and we go back to zero on the meter as well as zero on the scope. Here we are. Laser beam is back again, and then we get that same value again. Now, we're all familiar with absorption of light, and I just want to demonstrate it just for reference. I'm going to put a piece of glass in front of the laser beam, and we know that glass at normal incidence has reflectivity of about 4% per surface, so I should get an attenuation of about 8% or so when I put this piece of glass in the beam of light. Now you can see the meter has dropped now to 330, 300 and, well, if I can keep it still, 320 something. Now if I take the piece of glass away, you know, we go up to the previous number of 360 something. So you can see we have about an attenuation of about 8 or so percent. Now, what I'm going to do now is put this piece of glass before the detector also. And indeed, I'm going to hold it against the tube here so that I don't shake too much. And again, you can see that the attenuation is also about 8% or so. Here, let me put it in the front. And also then I'll put it in the back again, and hopefully I'll put it in the same position. You can see this. Oop. Hold it still. And then take it away. And then roughly we get this 8% attenuation. So now we've demonstrated that indeed light can be easily attenuated. Now we come to this crucial demonstration of gain. So now I want you to then watch both the scope and the meter as I turn on the amplifier. So here I'm going to now turn on the amplifier, and remember this number is around 363 or so, 364. Now you can see on the scope we jumped a little bit, and the meter has gone up to 380 something, which is an increase of about 5%. Let me turn it off. Again, you can see on the scope it went down. In fact, just watch the scope for a little while. I'm going to turn it on and off very fast so that you get a feel that here it goes up a little bit and down a little bit. Since it's only a few percent, it's difficult to see it on the scope the way I have it set up, but it's much easier to see it on the meter. So you can see that with amplification we have 380 something. With no amplification, then we're back to 360 something. Again, roughly it's about 5% amplification. Now you may wonder that maybe what we're getting is when I turn on the amplifier that we're getting light from the amplifier that hits the detector. It's not really amplification. So to prove this, what I'm going to do is block the beam of light going into the amplifier so that there's no light going on the detector. We're back to our 0 on the meter. And now what I'm going to do, I'm going to turn on the amplifier just by itself, just to see if there's any light from the amplifier falling on the detector. So here we go. Watch the meter and the scope. And here is the amplifier on. Again, you can see that there's no change on the meter or the scope. It's off. And do it again. On. And off. So indeed, we've shown that light from the amplifier or spontaneous emission from the amplifier is not hitting the detector and increasing the output. So again, let me just redo it again for you. Here is the light falling on the detector without amplification. Again, 360 something. And here comes the amplification. Again, so, yeah, it's close to 380. A little bit less than we had before. Maybe the amplifier is getting a little old. Here we are without amplification. We have this value. Now I hope you've become a believer in that you've seen for yourself that light indeed can be amplified. The last topic before we leave this session is on how does a laser start. You know, just because we have inverted population, we have between, let's say, level 3 and level 2, but how does a laser really start? We have gain, yes, but how does it get started? Because at the beginning there was no light at this frequency or wavelength. All right, there's plenty of pump light, but there's no light to start the stimulated emission going. But it turns out that the light that starts the laser going is spontaneous emission. Remember we talked before, when atoms are left alone in the upper state, they decay to a lower level and they can emit photons, all right, in all directions. Now, the spontaneous emission, that photon that is emitted along the axis of the cavity, that's the one that gets the stimulated emission going. And I show it here. Here is the spontaneous emission along the axis. It hits another atom here that's in the excited state, so it gets amplified, and then hits some more and gets even more amplified, and so on. As it goes backwards and forwards, then this builds up, and you get enough gain to overcome the losses, and the laser will oscillate. And if one of the mirrors has some transmission, then you get the output. So indeed, that's how an amplifier works, and that's how a laser gets started. And then when we come back for our next session, we'll talk about the laser beam properties and other properties, and so on.